In this video I'm going to talk about the chi-squared tests. I'm going to focus on the goodness of fit test and the independence test that can run through the contingency tables. I'm not going to look at the chi-squared distribution or the probability theories that are associated with that, but I'm going to focus on how to actually complete the tests using both Microsoft Excel and JASP software. The data I'm going to use is taken from the Statistics at Square One textbook by Campbell and Swinscoe. It's available either as a hard copy or you can read this online on the British Medical Journal website, who have kindly given permission for me to take some screen grabs so you can see, for example, this is the table of contents you can refer to, and we will be using the Chapter 8 chi-squared tests. I pulled the data out and there's a couple of descriptions that you can look at to get some context about the type of tests that we're working through and the underlying rationales. I would also suggest that you do take the time to read this in addition to watching the video, just to increase your knowledge around the area. The first test that I'm going to look at is the goodness of fit test on the 1 times 2 test. Now, when we describe a 1 times 2, what we're actually saying is that there are 1 row and 2 columns. And this naming convention follows for all the tests. So you might see 2 times 2, meaning 2 rows and 2 columns, or 3 times 2, 4 times 2, so on. What we're going to do is take the data that we put in and compare that to a hypothetical distribution. So in this case, we're going to look at the range that's within the chi-squared distribution, which is adapted from the normal distribution. Now, many people would look at 1 times 2 and say, well, if there's 1 row and 2 columns, that's only 2 numbers, and that's not enough to do a statistical analysis. And chi-squared allows this to happen by extrapolating where this would fit into the chi distribution. Let's look at a scenario. In the textbook, there is an outline that says that there is deaths recorded in a city 2 years in a row, and is there a significant number of deaths that are occurring? If you'd like to compare this analysis, it's important that you consider that there is no additional factors. They need to be independent causes of death in those years. So we couldn't have a natural disaster, and we couldn't have a sudden increase in the prevalence of a disease that would mean that there was a reason why these deaths had changed statistically. I've pulled the data into Microsoft Excel so you can see that we have year A and year B with 276 and 246 deaths per year respectively. And what we need to do is calculate our chi-squared value, look at the number of degrees of freedom, and use the combination to get the p-value using this command, which I'll talk you through shortly. To get these values, chi-squared value is the difference between the 2 observations squared divided by the 2 numbers added together. So let's have a look at how to do this in Excel. As we know, whenever we do anything in Excel and we want Excel to do a calculation, we hit the equals sign first. And I'm going to do this in double brackets, which is a little bit of overkill, but if anyone's not confident in the order of operations, it makes things a little bit easier to follow. So the first step is to get the difference between our 2 values. So I'm going to do 276 subtract 246. And I'll put that in brackets just to make sure that there's no confusion that it's not 276 subtract 246 squared. It's complete that difference and then square the answer. To do this in Excel, we need an upward chevron, which on my keyboard is Shift and the number 6, and the number 2, so that we know that the exponential is 2 to give us the squared value. And then I'll put another bracket there just so that we know we do all of this, and when we have the answer, that's what we divide. So we will divide, and just to know that we add them together before we use that in our division, I shall put brackets again. And so our final number here, 1.72, a whole bunch of decimal places. Now in chi-squared, to get the degrees of freedom, what we do is we look at the number of rows and the number of columns. Now, if either of that rows or columns is 1, we're going to use 1 for that value. If we have more, then what we do is we look at the number of rows minus 1 multiplied by the number of columns minus 1. So in this instance, 1 row, if I applied this formula, I would minus 1, that would give us 0. And obviously anything multiplied by 0 would result in 0. And we can't have 0 degrees of freedom. So I'm going to use 1 for this value. And in this instance, then we have two columns. 2 minus 1 is 1, and 1 times 1 is 1. If there was any more, if this was a 4 times 2, then that would be 4 minus 1 give us 3. 2 minus 1 to give us 1, so it would be 3 times 1 is 3. So I'm just going to type 1 in here. Now to change our chi-squared value into a p-value, we use the chi-squared distribution with a right tail function. If I start to type that in, you can see that Excel helpfully pulls up the options that start with that spelling. And if I double click on the option I want, it tells us the information we need. So we need our chi-squared value first. This is in bold. If I click on that and put a comma in, the next value comes in. It says I need this now, which is now in bold, which is our degrees of freedom. And this gives us a p-value of 0.189, which is well above the standard threshold of 0.05 for significance. Let's have a look at how this compares if we complete the analysis in JASP. I've already put the data in, so you can see we have the fact that we've got a city, year 1 and year 2, and 276 and 246 deaths. I'm going to use our contingency tables, and we'll put our deaths in as rows, our year in as columns, and our counts as our counts. And you can see the chi-squared value is 1.724, which matches what we got in Excel, and the p-value is 0.189, which again matches what we've got in Excel. It's obviously much quicker when we complete this analysis in JASP, but it's nice to work through the process in Excel so we understand what's happening and how we get to these numbers. Let's have a look at another type of analysis. If we have a little bit more data, then we refer to this as the n times 1 test. And n means this could take on any value. So this would be 2, 3, 4, 5, 6. And normally what you're looking at here is an observation versus a theoretical proportion. So in the textbook, the examples put that an order has been placed from a scientific supplier for 784 mice. Now, over time, a genetic theory of inheritance has been developed, and that suggests that 54% of the mice that are ordered will be pure white in colour, 40.8% will have a small brown patch, and 8.2% will have a large brown patch. Now, I've pulled these data into Excel, and I've put in the observed amount that we've got. So the order has been placed, and you've counted the mice and whether they are white, small brown patch, large brown patch, and the total does come to 784, and we have these observations. So what we need to do now is look at how we can complete this analysis. And step 1 is to look at what the expected values would be, because we're going to need this for our equation. So to do this, we're going to take our total amount, and obviously each of these proportions are always from this same total amount. So I'm going to hit F4 on my keyboard, and you'll see these dollar signs appear. That just locks this cell on here, so it knows that if I drag the equation around, if I drag the cell to copy this formula into other cells, to keep using this cell. And I'm going to multiply this by the first proportion, which is of the white mice, because we're looking for the expected values for white mice. Now this process in Excel, when you do this longhand, it doesn't like any of these values to be non-integers. So what I'm going to do is I'm just going to use the round function, and I'm going to tell it, don't give me any decimal places. Sometimes if you're using a command to get a value which will be used in further calculations, Excel doesn't like the output. So I always put these as absolute numbers. This just sometimes saves you a headache later on. If it's not going to make a difference or not be a problem, it won't change the outcome, but sometimes it saves you a problem, so I always do this to be safe. So here now we have 400, so we have a nice integer. I can drag this down, and because I locked that first number on, then even when I come down and look at where the final calculation was completed, you can see that the proportion changed, but the total it was calculated on did not. So this gives us our first stage. If we look at step 2, then what we need to do for step 2 is calculate the difference between the observed and the expected values. So here I have my observed minus my expected, so equals my observed, subtract my expected, and a difference of 20, as you can see, that's correct. And I can just drag this down, Step 3 is to take these values, square them, and then divide them by the expected, which I've replicated in this column title over here in cell D7. So we've already done the first part. I'm going to put that in brackets once again, even though it's not really needed, but it does help for anyone who's not confident in those order of operations. So I've taken this value, I've squared it, and now I'm going to divide it by the expected value, and then I can drag that down. So the final step that we need to do is get our chi-squared value, and this is simply the sum of the numbers above. So we're adding these values together, which gives us 2.875, and then I use the same command that I used in the previous example, that chi-squared distribution with a right tail, the x value. Then we're going to need the degrees of freedom. As you can see here, we had 3 times 1, 1, 2, 3 rows, 1 column. 3 minus 1 gives us 2, and we always maintain at least a value of 1. So therefore we have 2 degrees of freedom. This gives us a chi-squared value of 0.2375. Let's have a look at how the analysis compares when we use JASP. I've already set up the file, so I can import that quickly. We can see that we have the colour of the mice, the expected values that have been calculated by using the total of the observed amounts multiplied by the respective proportions. Now, when you have an observed count compared to a theoretical proportion, we use something called the multinomial test. We have a factor, which is saying how do we divide up our group. We have our observed counts, and it only asks for the expected count, so you need to use proportions to calculate those in advance. And when I drop those in, we can see that we have a chi-squared value which matches what we have in Microsoft Excel. Just increase the size so that's easier for you to see. And if I round up the p-value, you can see that that matches perfectly as well. Obviously much quicker when we use JASP, but the advantage of going through the process in Microsoft Excel is you understand the steps that it takes to get to the end result. I'm just going to close this down so that JASP is ready for our next example and come back to the slides. Next example I'd like to look at is the 2 times 2 test. And 2 times 2 tables are quite famous. There's a variety of different tests that you can do. They're very popular. And in the textbook there is this example when we're looking at the difference between a placebo and a medication and whether a patient on either the placebo or the medication dies or survives. I've pulled this into Microsoft Excel, so we're already set up to go. And before we start, I just want to actually guide you through the notation so you understand the following instructions. These values, the count values, are given A, B, C, D, and the totals are for rows specifically, columns specifically, or an overall grand total of everything. Okay. Now, when we calculate the chi-squared value, then we look at this process and we use these values to actually calculate the chi-squared number. To translate this into something that's usable in Microsoft Excel, we're going to end up with this equation. It's not vastly complicated, but it's long. So let's just have a look at how that works when we type this in. So I'm going to copy this pretty much exactly, so equals, and then I need 3 open brackets. A, if you remember, so that's our value 21, multiplied by D, subtract B, multiplied by C, and then I need to square that. Now I'm going to multiply all of that portion we've done before by this A plus B plus C plus D, which we know is our bottom corner here. Divide that, and then for this we want all of this to be together, so I'm going to put that in one big bracket here, and then our A plus B we know is this one, and that's multiplied by the C plus D, which we know is this one, multiplied by this, multiplied by this. Now I don't really need these brackets on here, and you can see that this is a slightly different format because these points here allow you to follow this first representation into this, but we've already calculated these as the total boxes. So that gives us our chi-squared value of 3.645, and we can use our chi distribution with a right tail once again to get our p-value. We can see here that once again it tells us what it wants. It wants our x value, then it wants to know our degrees of freedom. Now we've got a 2 times 2, and if you remember, the degrees of freedom says our rows minus 1 multiplied by our columns minus 1. So 2 by 2 changes to 1 by 1, which gives us 1 degree of freedom. So here you can see just above that typical threshold of 0.05. Let's have a quick look at how that compares to JASP, and then we'll have a look at how we can change this into confidence intervals. So you can see we have the same values here, 21, 110, 11, and 121. And we're back to our contingency tables here, our groups, our outcomes, our counts, and once again, our chi-squared value and our p-values are matching up perfectly. Now, at the moment, this current version of JASP doesn't give you the opportunity to get confidence intervals. And as I mentioned before, you can get a lot of information out of a 2 times 2 table. So I'm just going to guide you through another approach of how you could go about this analysis to identify if there is a significant difference. So the first thing we need to do is to calculate the proportions of each variable. And so we've got 4 numbers that we put in, 4 observations, and I'm going to get each of these divided by its represented total, so then we can get our proportions. I'm just going to change the layout of this slightly to make this a little bit easier to compare to the slide. So I'm going to put P3 and P4 in here. Now P1 we can see is our A divided by the total of A plus B. So we have A divided by the total of A plus B, and 2 is our B divided by the total of A plus B, 3 is our C divided by the total of C plus D, and 4 is D divided by the total of C plus D. So we've got our 4 proportions in here. The next step we need to do is calculate the differences between 1 and 3 and 2 and 4. So I'll put our differences over here, and the first one I need is the difference between 1 and 3, and the next one I need is the difference between 2 and 4, and you can see that these are the same number, just reversed. Okay, just either side, a negative and a positive. Okay, so the next thing we need is our standard error, and you can see that we've got this equation over here which is telling us how to get to that. So we need to do a square root at the start, and then what I'm going to do is put these bits in brackets just so that for those of you less confident of the order of operations, you can see exactly what stage is being done. And step 1 is our probability 1 multiplied by our probability 2. So probability 1 multiplied by probability 2, and that's divided by our A plus B total. Section that off so we can see we've got our first half, and that's going to be added to our probability 3 multiplied by our probability 4, and that's divided by our C plus D total. Close all of that off and we have a standard error of 0.04. So the final step is to get our confidence intervals, and you can see we've got our equation over here, so we've got our difference. So obviously I have 2 differences, our negative one and our positive one, so I'm going to do 2 sets of confidence intervals and look if that impacts on the interpretation. So for our first lower confidence interval, I'm going to take the first difference I calculated, and we have this symbol here you may not be familiar with. This means I need to do this twice. I'm going to subtract and I'm going to add, and in the instance of the lower confidence interval, I'm going to subtract that by 1.96 multiplied by the standard error. I'm going to repeat this process with the same difference, and then I'm going to add 1.96 times the standard error. Now what I'm going to do, because I'm sure there are some people who are wondering why I selected the first difference, I'm going to repeat this process with the second difference, and then we'll look at the interpretation of the confidence intervals together. So I will start off with the difference. I will then subtract 1.96 multiplied by the standard error, and then I will have the second difference plus 1.96 multiplied by the standard error. Now you can see that in both of these instances there is a confidence interval which includes 0. And if we look at these numbers a little bit more closely, we can see that as well as both straddling 0, they are in fact the same numbers just flipped around. We can see here we have minus 0.0016, and over here we have positive 0.0016. Same with the other numbers here, this 0.1555 and then the negative version. This is why we don't need to repeat the process. You're going to find that you've got the same range, just reversed. Now technically when we look at confidence intervals, we look at whether the confidence interval includes 0, and if it does we say that there's a significant difference. However, this is so close to 0, we couldn't really say that there would be a confident interpretation of a significant difference. And this is reflected on the fact that we are right on the threshold. Normally we would want to be below 0.05 at a p-value, and this is reflected in the closeness of these confidence intervals. If you're using the online version of the textbook to reinforce your learning, there is a different example of a 2 times 2 analysis. I've completed the analysis, which you can see in Excel here on the right. You can work through this in your own time just to confirm that you're getting the process correct. The final example I'd like to talk about is an n times 2 analysis. Although n represents any possible number, we've already seen a 1 times 2 analysis and a 2 times 2 analysis, so you can be fairly sure that when you see n times 2 analysis, it will be at least 3 rows and 2 columns, but it could be 4, 5, 6, however many that you actually have in your particular data set. There's a nice example that appears in both the textbook and on the online version of the textbook that outlines a scenario where a psychiatrist is looking at women that have admitted to hospital into either the gastroenterological unit or into the mental health unit with self-poisoning. And they've been divided up into groups based upon their husband's income or occupation. We're not going to worry too much about the reason of why this has been divided up this way. We just want to look at how we can apply the chi-squared test. There are some steps which you may recognize, as this is essentially the same as the n times 1 analysis, but we're just going to repeat this twice and then add up the 2 final columns. Let's have a look how we'll do that in Excel. So step 1, we first need to actually get the expected numbers before we can subtract the observed from the expected. And in this case, we're going to use our totals. We're going to have our row total divided by our total of the row totals. And that is not going to change, so I'm going to lock that by pressing F4. You'll notice the dollar signs have appeared. I'm going to multiply that by our column total. And again, that's not going to change, so I'm going to lock that in. Now I can drag this down. And then, of course, I need to repeat this process for the second row, because the first time I did this was purely based on the total of row A. Now I need to do that and repeat the process for the total of row B. And then I can drag this down. So the next step is to get the difference between our observed and expected. So I have my observed values here and I subtract the expected values, and this we can drag both to the side and down. So we can make Excel do the work for us if we lay out our spreadsheet quite intelligently. And as before, now we already have these values, so we just need to square these and then divide them by our original expected values. And once again, I can drag these both down and to the side. And so we've done exactly the same as we did with one column, just repeating this for both columns. We need to get totals of these columns. And it is the combination of these final two columns that gives us our chi-squared number. So here we have our chi-squared value. If you remember the process for degrees of freedom, we count up our rows. We have 5 rows, subtract 1, which gives us 4. We have 2 columns, subtract 1, that gives us 1. 4 times 1 gives us 4 degrees of freedom. There are some different commands I just wanted to bring to your attention. So obviously, so far, I'm completely relying on the right-tailed chi-squared distribution. There is a legacy chi-dist, and there is actually a left-tail version. So I can have chi-dist.lt. However, we should stick to the right-tail probability. This is the value that we're looking for. Let's just have a look how this compares to JASP so that we can confirm that we're getting the process correct. Here we can see our groupings and the wards which the patients were admitted to and the counts. So you can see that the data is input in a slightly different format than we can do in Excel, but this just allows us to ensure that our groups and our numbers marry up and that we don't get those confused. As before, we're working with the contingency tables. We use our rows and columns to divide our data up, and our counts are the observations that we've made. And we have a chi-squared value of 7.146, exactly the same as we have in Excel. And when we use the right tail version of the chi-dist command, we have 0.128, which is exactly the same as the probability which we get using JASP. This highlights why it's quite important to ensure that you use the right tail version, not the chi-dist, and not the left tail version. The textbook is a very useful resource. I encourage you to spend your time reading through that. If there are any questions or queries, please do post those in the comments.